Actually, we could solve Laplace's equation and Helmholtz's equation in those 13 coordinate systems, and so those were the ones that we spent our time working with. But we're going to look at primarily three. The one that you're most familiar with is the rectangular coordinate system. It's just x, y, and z, if you remember, the Cartesian coordinate system. And it's just, we set up an x, y, and z axis, just like here, and then you can find your point at, here's your point A up here. It'll be in terms of the unit vectors ax, ay, and az. So this one you're used to, you've worked with this one. There's nothing magic about this one. The cylindrical coordinate system may not be as familiar to you, but you've worked with it before, I know. Now here's where you'll have your confusion. You've got a phi down here. Now we have a rho, and rho is in, this rho is defined perpendicular to the z-axis. Do y'all remember what perpendicular means? What does it mean? 90 degrees out. Okay? 90 degrees out, and so it's perpendicular here. Now, so that'll be rho for us. Rho is going to be out, straight out. Phi is going to be measured off the x-axis along here, and it'll be measured towards the y-axis. Phi can vary from 0 to 2 pi. Z can vary from minus infinity to plus infinity, and of course rho goes out from 0 to infinity. And you can write your coordinates that way in terms of x and y. Rho is nothing but x squared plus y squared. See, rho is always measured in the xy plane. No matter where you are, rho starts at the z-axis and comes straight out to the point you're interested in. Phi will start along the x-axis and go out to a reflection of that point, and then z goes up. And so you can write your function, your a vector is an a rho, a sub rho, a sub phi, a little a sub phi. Remember these little a sub phi's with little hats on top, carets on top, are nothing more than just unit vectors. And since these are all perpendicular, now remember last time we talked about ax, ay, and az, right? And we talked about unit vectors, and you could draw a little circle of ax, ay, and az, and to determine whether or not you're going in the right direction, you just follow that circle, ax, ay, and az. Well, when you're working with dot products, remember what a dot product is? It's a reflection of one vector on another. The only time you'll get a value out of a dot product is when the vector is exactly in the same direction as the other vector. So a rho dot a rho is 1. A phi dot a phi is 1. A z dot a z is 1. If you take a rho, dot it with a phi or a z, it's 0, because they are orthogonal. So the dot product will only produce whatever is in the direction of that vector that you're dotting. Cross products, here's that little circle I was telling you about. Just write a rho, a phi, and a z, because that's the direction they'll be going in. So if you take a rho cross a phi, it'll be a z. If you take a phi across a rho, or a z, it'll be a rho. Now, what if I had a z cross a phi? What would that be? Minus a rho, wouldn't it? It's just going in the opposite direction. So just remember that, and I think it'll help you a lot. A rho, and you got a phi, and you got a z. And it goes like that. And if you'll just follow that direction, a rho cross a phi will give you a z. A phi cross a rho will give you a phi. If you flip it the other way, a rho cross a z, it'll be a minus a phi. A rho or a z cross a rho or a phi, it'll be a minus a rho. So just keep that in mind. You can do that with any one of these coordinate systems and it'll work. Now here's a little coordinate system transformation. Suppose we needed to go from the Cartesian to the cylindrical coordinate system. Your book, I'm going to let you use your book on these exams, okay? Your book has the transformations in there, but here's the deal. Here is ax and ay, and here's a point up here that's a phi, or a rho and a phi, okay? This is in the xy plane. So if your point is right here, if it was in Cartesian coordinate systems, it would have an ax component and an ay. If it's in cylindrical coordinates, it has an a phi and an a rho and an a phi component. And see the directions that they're going in. They're not going in the same directions. But if you took AX, this AX component right here, okay? If you took a rho and you picked off this AX component, here it is here. It would be, you got your a rho, it would be a cosine phi. If you want to know what is this component here in terms of a rho, it's the cosine phi component. Here's your a sub phi up here. If you wanted to know what your x component of this one here was, then that's going to be minus the sine of phi. Okay? If you came over here, that would end up being minus the sine of phi. And that's what this one is. And if you wanted to pick off the y component of rho up here, it's the sine component. There it is right there. And going back, going to the other one. Now, working with the phi component here, realize here's your sine of phi, and it's going in the negative direction, so you got a minus sine phi here. And then the same thing down here, you got a cosine to pick up the two components. That's the way you make your transformations. But let me tell you guys, once you've made them one time, you don't need to make them again. The book's got them for you. So what I would suggest you do is let's just use the matrices that the book gives you for these components. But I want you to understand where they came from. They're nothing but the reflection of one on the other. So you've got AX, AY, and of course AZ never changes in terms of the cylindrical coordinate system. So, but now we could go around and say, well, what if I wanted a rho? I want the a rho component, the little unit vector going in the rho direction. That's this one right here. Well, if I was going to do that, then I'm going to have to work with the other components, those two there. And I realized that the rho component right here is a cosine phi, and there it is right there. It's a cosine phi times AX. And this, in terms of the a sub y component, there's my a sub y component, it's a sine phi, and it just goes in over here. And I could do the same thing with the bottom term. Then I can get all these. So what are these? These are transformations of unit vectors. Let me tell you now that when you're working with a vector, you have to transform both the unit vector and the magnitude of the vector at that point. So we'll look at that in just a minute. But this is how you transform the unit vector. These are the unit vectors. These are these little orthogonal vectors that you're going to use to describe your system. And we can do the same kind of thing. These are your components coming down here. Here's your AX, cosine phi. There's your AY, sine of phi in the a sub rho direction. So here's what we're doing. If we want to know what is the component of A in the a sub rho direction, it's going to be AX cosine phi plus AY cosine phi, where these two are defined in the rectangular coordinate system. So you've got to make a transformation of those magnitudes. Same thing over here. We're just pulling those terms down and multiplying times your a sub x or your a sub y component.
What's the big A?
Sorry?
Big A, big X.
This is big A, yeah. This is the vector itself. These are unit vectors here. So you can have a vector AX, you can have a vector that's going in the AX, little a sub x plus AY, little a sub y plus AZ, little a sub z. But what if I wanted to convert that into a rho, a phi, and a z? This is the way you convert it.
So are the big AX, big AY actual number of the vector, the constant?
It could be a constant or it could be an equation.
Okay.
It sure can, yes. Sure can. Sure can. Okay. And here's a rho. Here's that component right here. Is right here. And what this tells you is if you have AX and AY and they're in the Cartesian coordinate system, but you need it in the rho coordinate, why would you care what coordinate system y'all work with? You say, oh, I don't care. Oh, yes, you do. Guys, when we get to Laplace's equations or some of these others, and you're going to try to solve those, if you're working with a cylinder and you try to work in rectangular coordinates, it's going to eat your dinner. I'm telling you, you're going to have some of the worst equations you've ever seen in your life. But if you work with them in cylindrical coordinates, they're really easy to work with. And then there's all kinds of spheroidal coordinate systems you can work with. When I was working in the Navy, we'd have underwater vehicles that I was trying to do a magnetic analysis on. And these vehicles would have not spheres, but spherical type of hulls. And man, trying to solve these equations were just terrible. So what you'd like to do is if you're working with a box or a rectangular waveguide, use rectangular coordinates. If you're working with a cylinder or a conductor that's cylindrical, then use cylindrical coordinates. If you're working with a sphere, then work with spherical coordinates. That's the idea. Okay. And these things, you can express these in matrix form. Now, do y'all remember how a matrix works? Oh, can I remember? Okay. What this is the x component, y component, and z component of the a sub rho term here. So here's my a sub rho term, and I go straight across here, and then this means to take this a sub x and multiply it by that term, take the a sub y, multiply it by that term, and take a sub z times that 0. Then for the next component, my a sub phi component, I take ax times minus sine phi, ay times this, and I just keep on going. And so that's just another way of writing. It's just writing in terms of a matrices. In terms of the little unit vectors here, what you're doing is you're taking your unit vectors, your ax dotting a rho and ax dot a phi. You're doing the same kind of thing with these. In other words, if you're trying to go back the other way, you can do it like this. And this is basically what it'll give you. It'll give you a sine phi minus a sine phi here. And a. So if I have a rho, a phi, and a z components, and I want to convert it to x, y, and z, I just take that one, multiply it times that one times that one times that, add them together, and I've got a sub z, a sub x. Do the same thing down here, and I get a sub y. Does that make sense? Do y'all remember doing all that stuff? Okay, good. I think most of this is probably a review. But there's a part of this that's kind of tough. Here's spherical coordinates. Here's your phi component. The same phi that you would normally have when you were in cylindrical coordinates is right here. It's measured off the x-axis. The difference is now I'm going to start at the origin, and I'm going to run an r vector all the way through my point. See, when I was working with cylindrical, I start here at the z-axis and come out with my rho vector. But now I'm going to start it at the origin and run it up to this point right here, and that'll be my r vector r. My phi component is measured off the x-axis. It's a reflection of this r vector back down here in the xy plane. And then theta is an angle measured off the z-axis. Now, so we want to make sure we kind of keep those straightened out. Here's what I want you to notice. When you have cylindrical coordinates, it's a rho, a phi, a z. When you have spherical coordinates, they're going to screw you up. It's going to be a r, a theta, a phi. Same a phi, okay, but it's not here anymore. And the reason I tell you that is because sometimes in some of the programs that's in the book that I'm going to have y'all run, for some reason, they flip those two things around. So if when you run this, you're going to be running MATLAB programs. When you run those MATLAB programs, if this doesn't come out right, now you need to check it by hand at least once in your life. But if you do it and it comes out wrong, it may be because those two have gotten flipped. Because I know in some of the programs they are. I'll try to make sure I identify those for you, but I know that's a problem at times. So you can define your vector A as having an a r, a theta, or an a phi component if you want to. And here's your magnitude of it. You take your r component, square it, plus your theta component, square it, plus your phi component, then take the square root of it. Right? And these are just dotting these things together. Remember, you can do the same thing over here. Rather than an a rho and a phi, you can have an AR, and you can have an a theta, and you can have an a phi. And you just go in that direction. If you go in that direction, it's positive. Go the other way, any other combination other than flowing in that direction, it'll be negative. And so here's your AR across your A theta. It'll give you an A sub phi because that's the right-hand rotation method. A theta, A phi, AR, same for the other terms. Okay? So all three of these coordinate systems are done the same way. And here's a point out here, converting between rectangular and spherical coordinates. Now here's your R. This R vector starts at the origin and goes to this point. It's going to have an X component, a Y component, and a Z component. In Cartesian coordinates, this is your transformation here. Your R now is equal to X squared plus Y squared plus Z squared. Your theta, which is the reflection off your Z-axis coming down here, so basically you go up here and reflected across, if you're looking for that angle theta between those two. It's the square root of x squared plus y squared, that is rho. So it's basically the inverse tangent of rho over z. And then phi is the other angle down here, and that's just going to be your y over x, inverse tangent of y over x. Phi does not change between cylindrical and spherical coordinates. Okay. Here's x. X is r sine theta cosine of phi. All right? So, and here's your r sine theta is right off here. There it is right there. Here's your r going up here. Here's your r sine theta right here. You're going to take that, reflect it all the way down here, and then you're going to take the cosine of the angle phi here to try to get your x component here. So what you do is you take your r going up here, reflect it back here, so you got this reflection down in the xy plane, and then you take the cosine of the angle to figure out what the x-axis is. That's the way those come about. You don't have to recreate those. I will assume that you all are bright enough to know how to work with them. So whenever you take these and put them all back together, your AX component right here, this little AX component along here, is equivalent to both an A rho, a phi, and an A theta component. But here are the transformations that you have to use with. And those things are a nasty game. Just nasty to work with. And AR, A theta, and A phi are done the same way. So they're just transformations back and forth. And the only way for you to get a good feel for them is just simply to work with them. Here, if you have a vector A sub r, now this is the vector, this is not the unit vector, these are all unit vectors right here. But if you have the vector A sub r, okay, Bill got to be here on time.
Yes, sir.
If you've got A sub r, A sub phi, and A sub theta, the way that it's converted from the x, the Cartesian coordinate system is ax times the sine theta cosine phi. That comes in from right in here. See, there it is right there. Your sine theta, sine phi's, here it is right here. Your cosine phi, there it is right there. So you see what we're doing, we're just taking those and we're dotting these terms together, and that's what you're going to end up getting. So these are nothing but just transformations that I want y'all to know how to use. Again, you may think, I'm never going to work with this. I'm going to make sure I don't. First job you get, I promise you, if you have that attitude, first job you get, they'll probably assign you to work with something like this. So I want y'all to make sure you know how to use it, okay? As an electrical engineer, you need to know how to use this stuff. Because most of the time, the systems you work with and the fields that you're going to be exposed to are never exactly planar with some surface. They're always at some angle out here. So here's my A component. In spherical coordinates, in terms of rectangular coordinates, here it is. It's AX times sine phi, cosine phi, AY times sine phi, sine theta, sine phi. So here it is right here. So what would you do if you had AX, AY, and AZ? How would you convert it? Well, depending on where you are in space, you have to know your point. You have to know your theta and your phi out there in space at that particular point. Then you take your AX component and you multiply by these, evaluated at theta and phi. Does that make sense? You got a place out here in space. It's an r, theta, and phi, right? And you want to convert your A vector to that point, at that point, to spherical coordinates. So to do it, you use the angle theta and the angle phi at the point you're interested in, okay? Substitute them in here and multiply them out. That's all you do. That's what this physically means. I don't think there's anything tricky about any of this, except it's just keeping up with all these different ugly terms. Now you can do spherical to Cartesian. Here's a conversion matrix. I like matrices, gang. I'm going to show you in a minute why I love them. Okay. I love the matrix. Now this takes all that stuff you and I were just looking at. It's absolutely terrible to look at. Eye burners that you don't want to spend a lot of time with, and you can easily convert them. And so how do I get A sub r out of here? I take my A sub x component and multiply it times sine theta sine phi evaluated where? Where? Yep, at a point out there, right? Evaluated at the point of theta and phi, wherever I'm at. Take my A sub y component times sine theta sine phi, and my A sub z component times cosine theta. So I'm going to do that. And then if I need A sub phi component, I do the same thing down here. I just Take those and lay them across here and multiply each one of those terms and add them together. So that's what I end up doing. And then here's a x, a y, and a z, right here. I can convert from a r, a theta, and a rho by doing the same thing. Take those and multiply them out. Do a matrix multiplication. And I can get my answers. And your book has conversions between Cartesian and spherical, and it's got all of them in there, which is really, really good. This is an outstanding book, by the way. I've used a lot of different books over the years, and there was a time when, I think I mentioned to y'all last time, there was a time which we didn't cover this stuff. We started right into electromagnetics. I started right into electromagnetics. Y'all didn't. And I found this out immediately. About a month into the semester, I gave the first test, and everybody just absolutely zeroed out on it. I didn't understand why. It was because they had not remembered the vector calculus. It wasn't they didn't know it, they just didn't remember it. So we went back, reviewed, and spent another month reviewing. Didn't cover very much in electromagnetics, but we sure did know vectors. So we'll do the same thing. And now what we're doing, we just do it at the beginning. We just use the textbook that has it in it, and it's really, really nice. Now, a lot of times you need to know the distance between 2 points because electromagnetics you may have a field at R1 and a field at R2, and you need to know the difference between those two distances. There may be some kind of charge located here. There may be a wire here, and you got another wire here, and you're picking up all kinds of interference here, and you need to know what the distance between those two happens to be, because you can then take your magnetic field equation and figure out how strong your magnetic field is at that point, because you don't know what the current is working there. So that's the reason we do this. So the distance between R2 and R1. Here's my distance squared. I'm going to take the way you're going to do it is you're going to take the x2 term minus the x1 term. The x, and it'll be times a sub x. And then you would take your y2 term minus your y1 term times a sub y, and your yz term, and your y2z term, and your y1z term. Take the difference between those, and then that would give you your actual vector d, and then you could square the magnitudes of those. That's what this is right here. Okay? This is just squaring the magnitudes. Here's squaring the magnitudes of this vector right here in Cartesian, cylindrical, and spherical. You're very familiar with this one. You know how to do that. How would you like to do this one or that one? Those are awful. They really are. But here's the good thing about it. You don't have to derive those. They're already done for you. But if you need the difference between two vectors and they're in spherical coordinates, then you just plug and chug right in here. If you need them in cylindrical, then plug and chug in cylindrical. Here's an example. You have a point. It's located at -2, 6, and 3. Can you tell me what coordinate system that is in?
Rectangular.
Rectangular coordinate systems. Important that you'll be able to recognize that. That one's obvious. And a vector A, which is y a sub x plus z a sub y. This may define a specific field that you and I are working with. Might be an electric field or a magnetic field. We want to express P and A in cylindrical and spherical coordinates. We want to evaluate A, this vector here, at P in Cartesian, cylindrical, and spherical coordinates. So, we want to, now let me ask you a question. When we finish evaluating A, if I looked at the magnitude of A, what would you expect for me to see regardless of what coordinate system I'm in? If I evaluated A, it doesn't matter what coordinate system I'm in, but if I do that, what would you expect to see? Wouldn't you expect to see the same value no matter what coordinate system you're in for the magnitude? But if you write the vector, it won't look the same, but it'll actually be in the same direction. Everything will be the same about it. It just may not look the same. So that's what we're going to do. So here's the first thing you do. Did we talk about this?
I think it went ahead a few slides.
I think I must have. There we go. Here's what we're going to do. To solve this problem, there's a two-step process that we need to follow. First thing we want to do, and you follow this each time, transform x, y, and z into rho, phi, and z. And then r, theta, and phi, respectively. So the first thing you do is you take the values x, y, and z and make this transformation. So let's do it. The second thing we want to do is once we've made the transformation, then you take AX, AY, and AZ, and then you transform them. So I tell you, this is what you and I were talking about at lunch. Okay? That's the process you want to go through. Step number one, let's do that transformation of X, Y, and Z, and here's what we're going to do. We want to go into cylindrical coordinates. We realize that in cylindrical coordinates, Z does not change. It's the same, so there it is. We go into our equations and we find that rho in cylindrical coordinates, now remember rho is the distance from the z-axis out. It is equal to the square root of x squared plus y squared. So I'm going to take x squared and y squared. Okay? We're going to take those values and square them, and there they are. I've squared my 2 here, minus 2 squared, my 6 squared, and there's my value, 6.32. Now my angle phi I get by taking the inverse tangent of y over x, and it's equal to 180 degrees. So there's my cylindrical transformation. So that's the first step you did. The second thing you're going to do is go into spherical coordinates now. Spherical coordinates, you've got to include all 3 points, the square root of x squared plus y squared plus z squared. And all I'm going to do this time in taking my square root is add that z term there, so it'll equal to 9, and I'm going to add that in. I'll get value of 7. Now I need 2 angles here. I need the angle theta. Now where do you measure theta from? It's measured off the z-axis. Okay. What about phi? What's this measured across? Between x and off the x-axis, right? X and y are down here, gang. Z's up here. Okay? X out here, y here, z. My head's sticking in the z direction. All right? Here we go. I know it seems stupid, but it's not because you'll remember it. I still have students that tell me about things I've done years ago, and I don't remember doing these things. They said, but I remember that. I said, well, good. If you remember it, it's worth my being stupid. So here's our theta. We can easily get that off here. Phi, I don't have to recalculate phi, do I? Already done it. It's 108 degrees or something, I think it was. Yeah, there it is up there. Why does this thing do this? Every once in a while, this thing wants to do. Okay. Well, here it is right there. 108 degrees. There it is. I don't know why the thing won't come down, but it should come down. But there it is. There are your values up there. Your value is 7, 64.62, and 108.45. Didn't do phi because phi was done in cylindrical, and I didn't need to repeat it. Okay? That's the first thing to do. Next thing we're going to do is transform AX, AY, and AZ into these other terms. Now, how do I do that? How do I transform this field here into a phi, a rho, a phi, and a z? Well, we're going to first realize that here's A. Oh, I guess we wanted to know these different values. A at point P is this. This is my, if I actually put my values in here, here it is here. There it is. So there's my value of A. Now here's what I've got to do. That's my actual value evaluated at A. If I want to go into a rho, a phi, and a z, what we're going to do is go back and take the matrix. And here's my matrix equation. Now what is that term right there? What is that y term? Why did I put y there?
It's the coefficient.
What is it? It's a sub what, Erica?
A sub x.
It is a sub x, right? There it is right here. There's a sub x right there. This one is a sub y, and that's a sub z. So here's a sub x, a sub y, and a sub z is 0. So I just put those terms in there. That's what I do. And then next, I got to expand this. When I expand it, here's what it looks like. I just multiply it out. Multiply those last terms out, that's what it looks like. And now I'm going to come back, and here's what I realized too. I realized that x is equal to rho cosine of phi, y is equal to rho sine of phi. I just put those in there. Okay? Just substitute those in. Now, when I take x and put these values into these equations right here, I'm going to now have the rho I need to put in here. I'm going to have the phi that I need to put in here, and z doesn't change. It's going to be 3. You see what we've done? We first took the matrix and we did the conversion. We put the AX, AY, and AZ terms in there, and we came out with these expressions up here. This just came from using your matrix transformation. Now then, for my y terms and my x terms and my z terms, I'm going to go back over here, and I'm going to try, if I can, to substitute in here my different values. And so that's what I'm doing. So I'm basically just going to make this transform here. My y cosine, remember y cosine of phi, this y term here was rho cosine of, rho sine of phi. So that's where all this comes from. And then, because I've got rho's in here, and I've got phis in here, I have to actually calculate out their values. And this process is real easy. This is a real good example to work with these on. So if I calculate rho, I've got a square root of 40, and an inverse tangent here is 6 over minus 2, and I can get the angle from that. If I expand all this stuff, here's what it leads to. Don't you love that? Oh, wouldn't you like to have to curl up with that every night and work on it? Yes, you would. Yes, yes, yes. Those are bad. Those are awful. And I know what you would do. You try your best to find a calculator that would do it for you, but if you couldn't, you do it with something else. So there's got to be a better way. There is, and we'll get to that in a minute. But all I've done now is just taken in every place there's a cosine of phi. I just put these values in here, multiplied them out. Now, do you know what the probability of you making a mistake is on this? 99%. Honestly, I very seldom ever do anything by hand that I don't make a mistake with. So you know where I'm going. Now let's do the same thing with spherical coordinates. The spherical coordinates, here's the same thing. This is a x, that's a y, and that's a z. I'm going to multiply that term right here, this term right here, and that term right there, and add them together, and that'll give me a rho, AR. I'm going to do the same thing again right across here, and it'll give me a phi. I'll do the same thing in the bottom. When I do, here's what it looks like. Okay, what am I going to do next? Well, I need to do something with these y's and x's and z's to convert them into r's and all these other things, right? Got to do something with them. So here's x. X is r sine phi, sine theta cosine phi. There's my y term, and there's my z term. Put them in there. Boy, that's looking good, isn't it? Yes, yes. It's really looking complicated there. Not bad now. Now here's the thing about it. This is not hard. Y'all hear me? It is not hard. It is complex, but it is not hard. This process is the same every time you do it. Except now, I've got to take my r's in terms of these and cram them in here. So there we go. Stick all those r's in there. And once I've done that, then I can put my points back in there. And there it is. Oh, my goodness. Mistake extraordinaire. I mean, man, this is hard to work with. But there it is. If you plugged all those values back in there, that's what you would end up with. You'd finally get an answer, but it'd be wrong, and then you'd figure it out. Hey, gang, that's the reason I don't take off very much for y'all making mathematical mistakes on the test. I take off for you making conceptual mistakes, but not for calculation errors when you set it up right. Because I understand. There are some professors that'll kill you half credit for that one if you happen to miss. You know, I think I told y'all when I was taking physics, God, I hated the guy. The professor I had was awful. He used mark sent sheets, and what that meant was you had 4 choices for your answer, and you marked one of those answers, whichever one could be the closest. And of course, he had every one of them was almost the right answer. You know, off one digit or change the sign or whatever. So if you messed up anywhere, you screwed up royally. The only thing I knew for sure was when I knew I missed it, because I had no answer that was anywhere near any of the ones he had. So I knew for sure I missed it. But he would do that, you know, and I just, it's almost impossible in engineering to do this at the level you're at now. And when you go to work, you're going to have somebody check your work. Your boss is not going to let you just turn your work loose and say, this is perfect, especially when you're fixing to stand before the sponsor and give him a briefing on what you're doing. Somebody's going to check your work to make sure, hopefully, that you didn't screw it up, because you will. And it's not because you're not smart, you're not good, it's just simply because it's so easy to make it. Now, remember what I said before? The magnitude of your A vector will not change. Notice it. Here it is in X, Y, Z. Here it is in rho, phi, and Z. Here it is in R, theta, and phi. It doesn't change. The magnitude is the same. Now, but if you looked at the vector itself, it looks different, but the magnitude does not change. And actually, if you look at the direction of it, the direction will still be in the same direction. It's just defined in different ways. And this is a terrible, terrible way to have to do it. I mean, it's awful. So here's my favorite, always, MATLAB. Okay? Why? Because let me show you how easy it is to do it. This is all you got to do to do it. Okay? You can just take these two equations right here. Here it is in cylindrical coordinates, using this R here and converting those over right there, and then you multiply it in there. Now, how do you solve the problem now, gang? If you had something like this. Now, these aren't the same values right here, by the way, but this is the equivalent. Here's your AX term, AY term, AZ term. How would you solve the problem? Then you're going to take that and plug it right in here, and then you're going to multiply those two together. And that's exactly what we're fixing to do. So here's your wonderful MATLAB equation, rectangular cylindrical. I put in X, Y, and Z. I convert to rho, phi, and this is in spherical here, it looks like. I think I've got both of them in here, actually. The first one I think I'll do is cylindrical, and then I'll come back and do a rectangle. Okay. So here are your values. I went ahead and calculated rho because I'm going to do the spherical next. So here's my R, rho, phi, and that should have been, yeah, this is the same thing. What I did is I converted it over to degrees right here is what I did. Okay. So there's your rho. No, I'm sorry, that's not. That's just rho, and it's not R. I was thinking that was R. But there it is. Now, all I've got to do, here's my matrix. See, that's all you do in MATLAB is you write it as a matrix, remember? Here's the first term, second term, third term in your first row. First term, second term, third term in your second row. Here they are. Just put them in there like that and multiply this one times this one right here. That's all you got to do. And it's done. And the sweet thing about it, it doesn't matter whether it's complex or it's not complex. Here's our ugly, okay? And here's the one I like. There you go. How long does it take me to do that? 5 minutes. How long would it take you to do that? 5 hours, okay? And most of you would be in and out of my office 14 times saying, there's got to be something wrong with the answer book. And there is. And it could be. But so, and you know, so I do want you to start doing this, and you will have some assignments where you'll have to actually use MATLAB on it. So I want you to do it. And here's the spherical transformation. Here's the old ugly here, and here's the way you convert it. You just convert your R's and your thetas and your phis, and there it is where you're going to plug those babies in there. And again, same thing. Now remember, when you're working with MATLAB, it's a higher order language. It works in C basically, but you got an A10-2 here. Now the reason you use an A10-2 is so to give you the right quadrant that you're in. If you just use A10, gang, it won't give you the right quadrant. But if you'll use an A10-2 and actually substitute in the right values in there, it'll solve it for you. And then you get your fees and all out of there. It'll put it in the appropriate place for you. If you don't, you're in trouble. And then all I did, here's my right-hand side over there. Here's my other terms here. Just multiply the two together. Okay. So here's my right-hand side. I've already calculated the values. Know what those are. Plug them in here. Here's my phi values. And I'm going to multiply right here. All I'm doing is multiplying. That's what that star means. And then, of course, here's the 14-day project there. And here's your 5-minute project over here. So the numbers on this doesn't matter. I'm just trying to emphasize to you the difference between the eye burners and doing what I'm trying to convince y'all to do. And I believe that most of you are beginning to believe me. That life is a whole lot better and a whole lot easier when you start using the tools that you have available for you. And I know in your math courses we don't encourage you to do that because we want you to learn how to do it. But in this particular case, I want y'all learning how to work with these. Now, I'm fixing to take you into something that's going to be hard, kind of conceptually, but you're just going to have to spend some time with it. We're going to look at constant coordinate surfaces. All right? And for example, the intersection of this is an XYZ plane, and that point right there is the intersection of a plane in the x-axis, up and down like this, up and down like this. This one right here is a plane in the x-axis. The plane in the y-axis, this one right here, and the plane in the z-axis, which is going up and down. And that one, that particular plane will give you a point right here of 0. Now, the intersection of only two of those, the x plane, okay? So here's a point over here in the x-axis, and then you've got one in the y, okay? You got one over here in the y, and what that's going to give you is it's going to give you, when you intersect this plane here with this plane here, it's going to give you a line that goes along parallel to the z-axis. Y'all see that? You got a plane right here, you got a plane right here, and the intersection of those two is a line that starts here at Q and goes all the way up here at P. Y'all see that? Okay. That's good. Now the intersection I just mentioned of x, y, and z would be that point right there. It's just a point. That's the only place those three different constant surfaces intersect. Now here's one that's a little bit more difficult. Here's spherical. In spherical, I can have a circular, I can have a cone, not a cone, I can have a cylinder out here that would be at r equal, or rho equal to a constant value. If rho is constant and you just spin it around, it could give you a cylinder, because you could be anywhere along the z-axis. And you could have any value of theta or phi. And then if you had a constant value of say, z up here, okay, some constant value of z, it would just give you a plane here. And if you have a constant value of phi measured off this x-axis as you're sweeping it around, it gives you that constant plane right there. So you have to think about it like that a little bit. The intersection of z equal to a constant, okay, z equal to a constant, it's going to be like right here, and rho equal to a constant will give you what? It's going to give you a circle. Where is the circle located? It goes right around here, right there. It's the intersection of the z equal to constant. See, z can move anywhere up and down, but it's a plane. And r equal to, or rho equal to a constant. The rho is a cylinder. If you intersect a cylinder with that plane, you form a circle, don't you? And that's what that is. If you have z equal to constant, phi equal to a constant, then you've got a semicircle line. And then, so we've got z equal to a constant, that's this one right here. And then you've got phi equal to a constant. So if you've got phi equal to a constant, so phi is out here somewhere out here. So what you would have then is the intersection of those two, and it would be a circle that would start here and run up to that phi. So it's like a semicircle. Okay? And it can go, you know, anywhere. So looking at these things is not always easy. Then if you look to the point, you got rho equal to 2, phi equal to 60, and z equal to 5. This is a point. Its radius from the z-axis is 2, its angle from the x-axis is 60 degrees, and how far up along the z-axis is 5. So that's all this means. Oh Lord, getting worse. In this case, r is equal to a constant, okay? If r is equal to a constant, r starts at the origin, and it runs out someplace, and if it's equal to a constant, and it can sweep in either direction like this, or up and down, it'll form a sphere. And this is the sphere right here. And the sphere can have any value, whatever the value of r is, that would be the radius of that sphere. So you can see you can have a sphere there. If phi is equal to a constant, okay, phi equal to a constant forms that plane right there. Okay? So there it is right there. And then, I mean, theta, I'm sorry, phi equal to a constant. Theta equal to, phi equal to a constant, this is theta. Phi equal to a constant is this cone up here. It's actually a cone. It starts at the origin, it goes up here, and it sweeps around. So it sweeps a cone out of this thing. These are not easy to see. I mean, you're just going to have to think about them a little while. Spend a little time working with them. And this is r equal to a constant and phi equal to a constant. So if r is equal to a constant out here, and if phi is equal to a constant sweeping around, then it's going to form this semicircle from here up to here, like this. Okay? So that's all it's saying. All right? And you can have other circles. And a point in the spherical coordinate system is defined by a 5, in this case a 5, an angle of 30 degrees coming down off the z-axis, and an angle of 60 degrees off the x-axis. And you would actually write it like this. So if I said, hey, what coordinate system are you in right here? What would you say? Spherical. Why? Because you got two angles on it. If you have one angle and another value here, what would it be? Cylindrical. Cylindrical, sure. Okay. All right, so that's all the magic for all this stuff. So these are, we're going to think about a little bit. First one's not hard. We've got two uniform vector fields. One is this E vector here. It's a -5 a sub rho plus 10 a sub v plus 3 a sub z. Now what this may be is an electric field. That electric field may be created by something is going in that direction, and you and I have a wire, or we've got a transmitter, or we've got a receiver, or we've got an amplifier sitting over there, and we're picking up this electric field. And we have currents flowing in our device that's creating this field right here, and we want to know how the two interact. Now, if I want this, if you see that information right there, tell me what it means. What do you do on the inside? E cross F, what does that mean? You're going to cross them, and it's going to be a vector. What does those two bars mean?
Magnitude.
Magnitude. Okay? So you're going to first find the vector, and then you're going to find the magnitude of it. So that's the first thing we'll do. To get the vector, remember we're going to write it a sub rho, a sub v, and a sub z. Why? Because I'm working in what coordinate system? Cylindrical. Okay? Cylindrical coordinate system. You know what's great is to give you a problem in cylindrical. This one's in cylindrical, and that's in spherical. That's a good problem. Oh, it is. Oh, Alex, you'll enjoy it. You'll learn so much on the exam, Alex. You will. Okay, so you better write it down. Huh? A rho, a phi, and a z. So how do we do it? We just slide those in here. Put this is your E in there. There's your E sub x term, E sub y term, E sub z term, and here's your F term. Put it right in here. And remember we have this, take the two columns over here. Cross in that direction is positive. Cross back like this is negative. And this is what we produce. Right? How do I get its magnitude? This is a vector. That's -66 in the a sub x direction, -27 in the a sub y direction, and -20 in the a sub z. So how do I get the magnitude? I take each one of those components and I square them. Okay? And take the square root of it. So there is 74.6. Yes, it is. Yeah, sure is. If this was a magnetic field and that was a magnetic field there, you know what it would have a tendency to do? It would have a tendency to take, if there was any wires in there, it would have a tendency to take those wires and twist them. These two fields, the curl of those two fields will give you a perpendicular force. And so when you curl them together, it will try to take the wires and twist them. So we're smarter than that. Remember last time? What we do is we'll take a motor and stick a shaft in there and put two fields on it like that and make it twist the shaft and it becomes a motor. It's exactly what we do. Sure. So reason this stuff's important. So here's your magnitude. That'll tell you that could tell you the magnitude of the torque that's actually on these two. You got these two conductors there. They've got electric or magnetic fields at that particular point. It's trying to shift them. It's trying to rotate them, and that may be the magnitude of the torque that you're putting on. Now, look at this next one. We want to determine the vector component of E at P, and remember this is 5, pi over 2, and 3. That is in cylindrical coordinates parallel, here we're going to go, to the line x equal to 2 and z equal to 3. When you look at that, your brain just goes into absolute, it just stops. Okay? It just does. So we got to think our way through this thing. So what we're trying to do is we're trying to find out, we want to know the component of E that's parallel. So if you've got a component and it's parallel to something, you're going to be doing a dot product somewhere in there probably, aren't you? You're going to try to find the vector that's going in the direction of this line right here. If you can figure out what direction that line's going in, you can. We'll come up with a vector for that, and you're probably going to dot it with this right here to determine the component that's going in that direction right there. And if you'll note here, the intersection of x equal to 2 and z equal to 3, okay, x equal to, let's see, x equal to 2, is that what it says? Yeah. X equal to 2, which is out here, suppose this thing is out here, and z equal to 3, okay, yep. That's going to give me a line that's going to be parallel. Remember we figured out last time? It's a line that's parallel here to the x-axis, or y-axis. So that's what that's going to be. So we've got x equal to 2 and z equal to 3. So if we look at the intersection of those two lines, or those two planes, it will give me a line that's going in the y direction here. Right? So that's what we're saying here. X and 2 is parallel to the y-axis, so the component of E that I'm looking for is going to be parallel to the y-axis. So how do I get it? So the component I'm looking for is parallel to the y-axis. Did y'all see how I got that? I'm sure you did, but it didn't register. Okay. If we've got a plane, an x, we're out here at the x, here's my x plane right here. This back plane, here's my x plane, and it's out a value of 2. Then my z plane, okay, my z plane is right here, and that z plane has a value of 3. So the z plane goes from plus and minus infinity, but it goes, its value does, but it's located at 3. So this intersection right here, that line right there is the intersection of a plane x equal to 2 and z equal to 3. And you see that it's forming a line here, Richard. Where's Richard? There's Richard. I was looking at you earlier and you looked like you didn't understand. So Richard, that intersection forms a line that goes into y-axis, along the y-axis there. Okay, let's do this again. Because I do want you to understand it. I do. How can you tell me where the x equal to 1 or x equals 0 plane is? X equals 0. X equals 0 plane is right down here, right? Because x is equal to 0 right there, right? Did y'all buy that? Okay, so it's x equals 0 plane right down there. Right? So there it is there. It's going down like this, but it's right here, along here, and it's going down. It's x equals 0, so it just goes to infinity in every direction, but it's located at x equals 0. Now what about the z equal to 0? Z equal to 0 would be also, remember z equals 0, it has a value of 0. It can't go up, it can't go down, it's got to be a 0. So it goes out into infinity in all directions. And if this was at 0 right here, that point was actually 0, the intersection would be that line right there, because you got this x equal 0 line, your z equals 0 line, and the two are plane, the place where the intersection is right there. It just forms a line. And then from right? You got it, Richard. All right, good, man. Now, if y'all don't understand, guys, it's worth it to go over. And in reading these problems, it's going to take a little while for it to grow. So the component of E parallel is given by this right here. Now, remember I told you that what we want is we want the component in the a sub y direction, and the way we get it is to take take E, and we're going to dot it with a sub y. Because that'll give me the component that's reflecting along that direction, right? Now, do not forget this right here. Y'all will dot it. I've seen it happen time and time again on your homework, on your exams. You will dot these two together and forget to put that term on. Don't do that, okay? Because that tells you the direction Mike is going in, okay? Dot product is a scalar. Sure is. But it's a scalar that tells you the component that goes in this direction right here. So in order to make a vector out of it, you've got to add this term back to it to tell it what direction it's going in, I tell you, or you won't know. Okay? Now, at these values right here, we're looking at those 5, I, 2, whatever. We're going to substitute, here's my a sub y component right here. But I need to substitute in some values in there. So I'm going to put in power 2 for phi, and I don't need anything else up there because this doesn't need it. Here's my a sub y component, but I want to convert it over. So if I put these terms in here, convert it over to a sub rho and a sub phi, if you'll notice that cosine of power 2 is 0, and this is 1, so I just get an a sub rho out of that thing. So I can rewrite this then, if I wanted to, is just minus 5, and I multiply this out, and I take this component up here, get what I'm doing here is I'm trying to convert those over, and if you'll realize that my a sub rho and my a sub phi, or x, y, z components are the same. So right down here, I've got a minus 5 a sub rho. All I did was take that one term off there because a sub rho and a sub y, in terms of this equation here, are the same. This and this are actually the same. So I just pull that term right down here, or it's the same as minus 5 a sub y. At that particular point, that's my value. Yep, if you're allowed.
Previous slide, how come there's no X of Z over
Ace of what?
there? X of Z.
There is an ace of Z term, but it's not for what we're looking for. What we're trying to do is find the reflection of E on the line x equal to 2, or on the intersection of x equal to 2 and z equal to 3. See, what we're doing is there are other terms we could work with. Yeah.
Second step, you convert it to
This one right here.
cylindrical, yeah.
Because cosine of that value right there is 0.
That's ace of T.
Ace of rho,
Ace of Z.
where's ace of Z?
That's what I'm asking. It's not
There isn't one.
Oh, there isn't one.
So is it equal
See,
to
for ace
zero?
of y, I don't need an ace of z term. See, ace of z, in terms of cylindrical coordinates, ace of z and rectangular, ace of z and cylindrical are the same values. I tell you, I can put an ace of z on here if I want to. It won't matter because I don't have anything to multiply by. Okay? See, that when you go from rectangular to cylindrical, there is no, the ace of z's just stay the same. You don't convert them over. But it turns out there is no ace of z component here. It's just ace of y's. And so that's, and so in order to multiply this all out, I had to convert this over and put these values in here. And then I could take this term right here and dot them out. And when I did, I was able to get out this minus 5 ace of rho. Now, there could be other intersections that we would have an ace of z component on. We absolutely could. But just not for this one.
So I have the ace of rho.
Yes, sir, you have an ace of rho. Turns out ace of rho and ace of y are in the same direction. That's the only reason. Okay? And the only reason we know that, I tell you, is at that particular point in space, when I put my values of phi in here, or theta in here, no, it's phi. Phi. When I put phi in here, this other term dropped out, and the only thing I was left with was ace of rho. It's just a mathematical, this one just came out this way. Normally, yes, sir, you would have other terms in there. There would. All right. Now we want to find the angle E, the angle that E makes with the surface Z equal to 3. The angle that E makes with the surface Z equal to 3 at P, at point P. So we've got E is here, is equal to minus 5 ace of rho plus 10 ace of phi. All right, we want to find that out. All right, what is it? Note here that Z equal to 3 is a plane that's located at Z equal to 3 here that goes to plus or minus infinity in the x and y direction. So it's just a plane. What we want to do is we want to find out what is the normal to that plane. Right? I'm trying to find out the angle that E makes with the surface. So in order to determine that, what you and I normally do, if we have a surface like this, what we normally do is try to find a normal to that surface. And then, if I've got an E vector that's coming through like this, then how can I find out what the angle is between here and here? How do I get that angle? I can use a dot product. Or I could use it depends how I want to do it. I could use a cross product kind of deal. But a dot product would definitely give me that angle right there. If I knew what the normal was to this surface here, this is the Z equal to 3 surface. Right there. It just happens to go through Z equal to 3. It goes to X and Y, infinity to X and Y. If I know what that is, if I can get the normal here, I can dot the two together, and I can get my answer. So that's another way of doing it. So here we go. Since always, gang, any of the planes that you have, if it's an X plane, that means the normal to it is in the X direction. If it's a Y plane, constant plane, it's going to go in the Y direction. If it's a Z plane where it's a constant surface, it's a Z plane, it'll go in the Z direction. So the normal to this Z plane located at 3 here is going to be a sub Z. And what I want to do is take a sub Z and dot it with that E vector. How do you practically use this? I've got an antenna. Here's my antenna surface. I've got a field that's propagating in here from somewhere else. And when that field hits the surface of this antenna, the only part of the field that this antenna will pick up will be the normal part, this part right here. Normal component. I'm going to pick up the rest of it. Remember I told y'all last time, if you took this thing and turned it at 90 degrees to the plane of that surface, you'd pick up nothing. It's called polarization. So that's the reason this is important. So we take our E vector here, and in terms of dot products, I'm going to take the magnitude of this vector times the magnitude of that vector times the cosine of the angle between them. The problem is I don't know what the angle between them is. But I sure know what everything else is. What's the magnitude of A sub z? The magnitude of A sub z, what is it? 1. It's a unit vector. What's the magnitude of E? Well, I find out. I take the square root of 5 squared plus 10 squared plus 3 squared, and that gives me the square root of 134. The only thing I don't know up here is cosine of theta. So I can dot all these, I can dot those together, when I dot those two together, I'm going to get a value 3. Here, when I dot A sub z, with this function up here, the only term that comes out of it is that one term right there. When you dot E, that vector there, with A sub z, it pulls out that A sub z term. There it is, 3. When I take the magnitude of E, squaring that term, that term, that term, add them together, taking the square root of it, I get that. So I can solve that problem. The angle is 74.98 degrees. And then that's going to be the angle between the two. And then at z equals 3, we can substitute in. I'm asking it for the plane with the surface. I was wondering why we went to 90 degrees. That tells me the angle between the perpendicular, but if I want to know the surface, that's this angle down here. I'm going to have to just take 90 degrees and subtract that from it. See, the angle I found was this angle right here. But the angle that I'm looking for is this one here. So you can read these things very, very carefully. Really carefully. Ooh, spherical quantities. We want to determine D, that value there, at these points. How would you do it? Do what? Plug and chug. Absolutely right, how you're in business, man. Just plug in R, plug in phi. You know, you can do that. There it is right there. Plug it right in there. No problem. You get a -5, a 0.043, and 100 here. Now, make sure, gang, when you're doing these calculations, you realize that, that these values here, this is not an angle anymore on this right here. It's the actual value in the A sub phi direction. Now, these are all angles here. You can have angles on them, but those are actual values in that particular direction. All right, now the component, this is a bit harder. The component of D tangential to the spherical surface at r equal to 10 at P. Tangential, what does it mean? Every point that has a surface has two components. It has a tangential component and a normal component. It can have more than one tangential component, but it cannot have more than one normal component. Well, it can have a plus or minus. But every surface, every vector can be broken down into, we're going to look at this, D can always be D sub n plus D sub tangential. If you have a surface, if you go perpendicular to that surface out into space, I mean perpendicular in every way, that is your normal component. If along the surface here, this is, maybe I should go up. But on that surface, if you're trying to go right along the edge of that surface, that's your tangential component there. Okay? And you may have two of them. You may have an x and a y component here, an r and theta, whatever. But you can have two components. And what we want to do is we want to find the component of D that's tangential to the spherical surface r equal to 10. Now tell me about a spherical surface. That spherical surface means you go out to a radius of 10 and you sweep a sphere, a complete sphere in every direction at r equal to 10. Do what? All right, crossing, cross product. That sounds like a good idea. I like that. Right? Absolutely. We're going to look at that. Now, this is what I just mentioned. Any vector can always be defined in terms of an orthogonal component. Normal component, tangential component. So, if you and I can get the normal component, which is a lot easier to get, we can subtract it from this value right here, and we can get the tangential component. Or, if it's easier to get the tangential component, then subtract it from this and get your normal component. So you don't have to have them both. You can just simply work with one and then get the other. So that's what we're going to do. So the normal component to the surface at r equals 10. Can you tell me what a normal component would be anywhere along that spherical surface right there? What direction would it go in? A sub r. That's the direction, right? This is a spherical surface, so the normal component to a spherical surface is in the r direction. What's the normal component of a surface that's a phi equal to a constant phi surface down here? It's going to go in the phi direction. If it's a constant theta surface, it's going to go in the theta direction. That's the normal component, okay? Each time. All right. So here's our normal component right here. How do I know this is my normal component? Well, heck, I just go up here and pull off here's my normal component to this surface at that point. Right? Y'all see that? Because the spherical surface here is constant. And I want to know, right now I'm going to try to work with the normal component, and then from it I'm going to subtract it from the original function and get my tangential components. So basically, which I could almost do by looking at it, but basically then, so my normal components will be this a sub r term right here. That's my normal components. Here it is. So it's minus 5 a sub r. If I want to know my tangential components, it's whatever's left over. Those are my tangential components right there, aren't they? It's just my original b minus this right here, and that gives me my other terms. And then all I do is substitute in the values for it, and that's my balance. Y'all get the concept now of normal and tangential, because everything has them. Any surface you have will have them. The hard part is figuring out what they're asking you to do.
Does it leave you with a plane?
Pardon me?
Does it leave you with a plane?
Yeah, it does. Well, it's actually a line, I guess, that goes in that direction, because it doesn't go all the way to infinity, but it's located, it's a plane that's located at that point there, along that line. Okay. Now we want a unit vector P perpendicular to D and tangential to the cone theta equal to 150. This is an awful problem. Yeah, it kind of is. Okay. But it's really not if you'll stop thinking about it. Now here's what I want. I want a vector P that's perpendicular to D. All right? Perpendicular to D. Y'all know where D is going? Well, we know what it says. You think you could just draw one perpendicular to it? Heck no. That'd be a much difficult thing of your life, trying to visualize it. You can't visualize it. And you just can't. You'd have to walk along it before you could visualize it. So you want a unit vector P perpendicular to D and tangential to the cone theta equal to 150 degrees. Here's the cone right here. The cone is at 150 degrees. It's going around here. Here's your point right here. Okay? Now, I want a vector perpendicular to D and tangential to this cone right here. That's what I want. So, how are we going to do that? What does it say? Okay, so it'll be tangential and perpendicular. Is this right? Yeah, this is a constant thing. Yes, it is. Okay. I have it kind of drawn on it. Yeah. So, it seems like there's something wrong. It's perpendicular to D, that I understand, and tangential to the cone. All right, if it's tangential to the cone, is that what it asked for, or did I write this thing wrong? Tangential to the cone. Yes, thank you. Thank you. Ty is exactly right. That was my problem, Ty. I was really having a problem with this. All right, now look. If I want something that's perpendicular to the D vector, and I don't know what direction it's going to be in, but it's got to be perpendicular. It's got to be tangential to this cone up here. Can you tell me what the normal component of that cone is? It's a sub theta. That's the normal component, right? That's what this is right here. This is a sub theta is the normal component. If I take D and I cross it with a sub theta, do you know what I'll create? I'll create a vector that is what? It is perpendicular to this one, right? Perpendicular to D, and it's perpendicular to a sub theta, right? It's perpendicular to both of them. Draw by that. Okay. Since this is normal to the cone's direction, normal coming out here, then the vector that I end up with has got to be tangential to that surface. Don't you love it? Of course you don't. Hey guys, I'm expanding your horizons. I'm making you guys the big thinkers. Okay? But that's what we do. Now that's the way you're going to have to think your way through these problems, because they're not hard, but they just take some time to think your way through. And then what I'm going to try to do here, then it asks for a unit vector, I think was the last thing. And the unit vector just simply takes the D cross your a sub theta and then just divides through by the magnitude of where you go. Okay? That is the most difficult problem you will face. I don't think you'll face any. This is some example of this in the book. But I don't think any of them that I've given you for homework is anywhere near that difficult. Hopefully. Of course, if you can't see them, they're all impossible. Okay. All right, questions? So here's what we've done. We basically, in this particular chapter, in the last chapter, we talked about what? Tell me. Vectors. We talked about unit vectors. We talked about, what is a unit vector? What is a unit vector? Well, I've already erased it. That's right. And it has a magnitude of 1. It's the direction that you're interested in. So you take the vector itself and divide it by its magnitude. And it'll give you a unit vector. And then we talked about taking dot products, and a dot product reflects one vector on another. It's very, very important to us. Because for us, energy is coming in here on this, trying to get into that surface there, and only the energy that comes in like this to it will go in. If it comes in like this, it's really going up like that. It's not going to go in there. And so the curl is another one. Taking your curl of things. That's the rotation of things. So chapter 1 was just a brief review of a little bit of vector calculus. This may have been a little bit different. This is transformations. Now, most of this stuff is cookbook. It's in the book. But when you're asked questions like this, it is not cookbook. You really do have to think your way through this. Okay. All right. I will not be here Monday, so there won't be a class Monday. I've got to go out. I've got to go to some other schools and do some. I've got to try to do some recruiting. But anyway, we didn't know that it was going to occur on Monday, but it is. So there won't be a class on Monday. But we'll have a test on Wednesday. It'll just be on these 2 chapters. Very similar to your homework. I don't have to make it hard. It's already hard. I don't. You can use your book, but you can't use you can't use any notes and anything like that. But you certainly can use your book. Okay? Any questions now? I'll be available between now and then to help y'all in any way I can. So make sure that you can email me. You can come out and see me and call me on the phone, whatever. So, any questions? All right, gang. Make sure you sign in, and if your name's not on the roll, make sure you put your name on the